Imagine a world where every time you needed to use a computer, you had to own the machine yourself, keeping it in your home or office, plugging it into the wall, and updating it on your own. For most of computing history, this was the norm. Organizations had to buy their own servers, maintain them, and ensure they were always running. If you needed more computing power, you bought more hardware. If you needed less, the extra machines sat idle, quietly gathering dust but still consuming electricity and attention. All of that began to change with the advent of cloud computing, a shift so fundamental that it has become the backbone of modern technology. At its core, cloud computing is the delivery of computing services, such as servers, storage, databases, networking, software, and more over the internet, rather than from a local computer or on-premises server. The United States National Institute of Standards and Technology, or NIST, provides a widely accepted definition that serves as the benchmark for understanding this field. According to NIST, cloud computing is a model for enabling ubiquitous, convenient, on-demand network access to a shared pool of configurable computing resources like networks, servers, storage, applications, and services that can be rapidly provisioned and released with minimal management effort or service provider interaction. This definition, authored by Peter Mell and Tim Grants, is intentionally broad, allowing for comparison across all types of cloud services while still highlighting their unique qualities. To understand why cloud computing is such a dramatic departure from the past, it helps to look at its origins. The seeds were planted as far back as the 1960s with the development of time-sharing systems. At that time, computers were enormous and expensive, so people began to explore ways for multiple users to share access to a single machine. Time-sharing allowed several individuals to use a mainframe computer simultaneously, each receiving a portion of its power. While this concept was a far cry from today's cloud, it introduced the idea that computing resources could be shared among many users, an idea that would resonate through the decades. The journey from those early mainframes to today's cloud landscape was a winding one. In the 1970s, the now familiar cloud symbol began appearing in diagrams representing complex networks whose inner workings were hidden from view. The 1980s and 1990s saw the rise of virtual private networks and the World Wide Web, each adding new layers of connectivity and abstraction. In the years that followed, new forms of computing emerged: distributed systems, where computation was spread across many machines; cluster computing, which linked multiple computers to work on a single task; and grid computing, where geographically dispersed resources were pooled to solve large scientific problems. Each of these developments chipped away at the old model of computing as an isolated, on-premises activity. By the early 2000s, the stage was set for the emergence of cloud computing as we know it. Technology giants began offering services that allowed organizations to rent computing power and storage by the hour, instead of owning and maintaining their own hardware. Amazon Web Services, Google App Engine, and Microsoft Azure all launched during this period, making it possible for businesses and eventually individuals to access robust computing resources over the internet. This shift marked the true dawn of the cloud era, and it continues to reshape the technology landscape today. But what exactly sets cloud computing apart from traditional computing models? At its heart, the difference lies in how resources are delivered, managed, and paid for. In traditional computing environments, organizations buy or lease physical hardware and house it themselves. They are responsible for operating, maintaining, and upgrading these systems. This approach can be costly, inflexible, and difficult to scale. If a company suddenly needs more capacity, say, to handle a holiday shopping rush, it must invest in new servers, set them up, and hope that the increased demand lasts long enough to justify the expense. If the need for extra power fades, those servers become underutilized assets. Cloud computing flips this model. Instead of purchasing physical infrastructure, users access computing resources as services over the internet. These resources are hosted in vast data centers, managed by specialized providers. Organizations can scale up or down as needed, often with just a few clicks or even automatically. They pay only for what they use, much like utilities such as electricity or water. This pay-per-use model offers greater flexibility and can lead to significant cost savings, especially for organizations with fluctuating demands. The National Institute of Standards and Technology identifies 5 essential characteristics that define true cloud computing. The first is on-demand self-service. Users can provision resources such as server time or storage as needed, without requiring human intervention from the service provider. The second is broad network access, meaning services are available over the network and accessed through standard mechanisms, typically using the internet and common devices like laptops and smartphones. Third is resource pooling. The provider's computing resources are pooled together to serve multiple customers, with different physical and virtual resources dynamically assigned and reassigned according to demand. This model leverages multi-tenancy, where many users share the same physical infrastructure while their data and services remain isolated from one another. The fourth characteristic is rapid elasticity. Cloud services can be quickly scaled up or down, sometimes automatically, in response to changing needs. From the user's perspective, resources often appear unlimited and can be appropriated in any quantity at any time. Finally, there is measured service. Cloud systems automatically control and optimize resource usage by leveraging metering capabilities. Usage is monitored, controlled, and reported, providing transparency for both the provider and the consumer. In addition to these characteristics, the National Institute of Standards and Technology describes several service models that capture the different ways cloud computing resources can be delivered. These are commonly known as infrastructure as a service, pronounced IaaS, platform as a service, pronounced PaaS, and software as a service, pronounced SaaS. In the infrastructure as a service model, users rent fundamental computing resources such as virtual machines, storage, and networks. With platform as a service, the provider offers not just infrastructure, but also platforms, like operating systems and development tools, enabling users to build and deploy applications without managing the underlying hardware or software. Software as a service, meanwhile, delivers fully functional applications over the internet, which users can access from any compatible device without worrying about installation, maintenance, or updates. Cloud computing also comes in several deployment models depending on who owns and operates the infrastructure and who has access to it. These include private clouds, operated solely for a single organization, public clouds, available to the general public or a large industry group and owned by a cloud service provider, community clouds, shared by several organizations with common concerns, and hybrid clouds, which combine two or more distinct cloud infrastructures, allowing data and applications to move between them for greater flexibility. What truly empowers cloud computing are its underlying design principles. A few key principles stand out. Federation is one, the ability to connect and interoperate between different cloud environments, which can be critical for organizations with complex needs. Independence and isolation are also important, ensuring that each user's data and workloads remain secure and separate from others, even when sharing physical resources. Elasticity, as discussed earlier, gives the cloud its ability to dynamically expand or contract in response to demand. Business orientation reflects the fact that cloud services are often designed from the ground up to align with business needs, offering customizable pay-as-you-go options. Finally, trust is fundamental. Users must have confidence that their data is secure, their services are reliable, and their provider is transparent. When compared with traditional information technology infrastructure, the differences become even clearer. Traditional information technology is typically capital-intensive, requiring significant upfront investment in hardware and software. It is often less flexible, since scaling up or down involves purchasing and installing physical equipment. Maintenance and upgrades are the user's responsibility, which can be both time-consuming and costly. Cloud computing, on the other hand, operates on a service model. Costs become operational rather than capital expenses, since users pay for what they consume. The responsibility for maintaining and securing the infrastructure shifts to the cloud provider, freeing organizations to focus on their core activities. Another notable difference is accessibility. Traditional information technology systems are usually housed in a specific location, such as a corporate data center. Accessing them remotely can be cumbersome and often requires specialized solutions like virtual private networks. Cloud computing, by contrast, is designed to be accessible from anywhere with an internet connection. This broad network access has become even more significant in recent years as remote work and global collaboration have become commonplace. The evolution toward cloud computing has also been shaped by advances in automation and security. Cloud-native architectures are built to be scalable and resilient, able to recover quickly from failures and handle unpredictable spikes in demand. Automation makes it possible to deploy, manage, and monitor resources with minimal human intervention. Security, once seen as a potential weakness of the cloud, has become a core focus, with providers investing heavily in measures to protect data and ensure compliance with regulations. Of course, the shift to cloud computing has not been without its challenges. Organizations must weigh the benefits of flexibility, scalability, and cost savings against concerns about data privacy, security, and control. For some, especially those with strict regulatory requirements or specialized workloads, traditional on-premises infrastructure may still be the best fit. For most, however, the cloud offers a compelling alternative, one that brings innovation, efficiency, and new possibilities. In summary, cloud computing represents a profound change in how we think about and use technology. It builds on decades of progress, from the early days of time-shared mainframes to today's global networks of virtualized resources. Defined by its on-demand, scalable, and measured approach, cloud computing frees users from the constraints of physical infrastructure and opens the door to new ways of working, collaborating, and creating. As technology continues to evolve, the foundational concepts of cloud computing remain central, shaping the digital world we live in and powering the innovations of tomorrow. Imagine for a moment the world behind the cloud services that power everything from your favorite streaming platforms to the tools businesses use to manage their operations. Beneath the surface, the cloud is not a single uniform technology, but a flexible ecosystem of models and services, each with its own purpose, strengths, and trade-offs. To truly understand how cloud computing supports such a wide range of needs, it is essential to explore the core service models. Infrastructure as a service, platform as a service, and software as a service, as well as the deployment models that determine how and where cloud resources are provided. At the center of this ecosystem are the service models that define the types of resources and levels of control available to cloud users. Infrastructure as a service, or IaaA, forms the foundation on which many other services are built. With infrastructure as a service, organizations can rent virtualized computing resources such as servers, storage, and networking on a pay-per-use basis. What makes infrastructure as a service particularly appealing is the degree of control it offers. Users can install their preferred operating systems, configure their own middleware, and deploy any applications they need. This flexibility makes infrastructure as a service a popular choice for businesses that require custom environments, want to test new software, or need to quickly scale infrastructure for temporary projects. The practical impact of infrastructure as a service is significant. By shifting the responsibility of maintaining physical hardware to the cloud provider, organizations can focus on configuring and managing their virtual resources to meet specific needs. This model is ideal for startups experimenting without investing in their own data centers, as well as established enterprises looking to expand their capabilities. In real-world terms, infrastructure as a service is like leasing an empty warehouse. The tenant decides how to organize the space, what to store, and how to operate, while the landlord maintains the building itself. Moving up the stack, platform as a service, or PaaS, removes even more of the underlying complexity. With platform as a service, the cloud provider not only supplies the infrastructure but also manages the operating systems, development tools, database management, and other software needed to build, test, and deploy applications. Developers can focus on writing code and designing user experiences instead of worrying about hardware failures, software patches, or network configuration. This model streamlines the software development process, reducing the time and expertise required to bring new applications to life. Platform as a service is especially attractive for teams seeking efficient collaboration. The environment is standardized and automatically updated, ensuring everyone works with the same set of tools and dependencies. Use cases for platform as a service include building web applications and APIs, supporting big data analytics, or enabling Internet of Things solutions. Because the platform handles much of the operational overhead, development cycles can accelerate, and small teams can compete with larger organizations. While this comes at the cost of some control, the platform determines much of the environment's configuration. The benefits of speed, simplicity, and scalability are often decisive. Then there is software as a service, or SaaS, which is perhaps the most visible form of cloud computing for everyday users. In the software as a service model, the provider delivers fully functional software applications over the internet. Users access these applications, such as email, customer relationship management tools, or office productivity suites, through a web browser or a dedicated client. There is no need to install, update, or maintain software locally. Everything is managed by the provider and delivered as a service. For organizations, software as a service provides immediate access to advanced solutions without the need for in-house expertise or infrastructure. It enables businesses to respond quickly to changing requirements, support remote or distributed teams, and scale usage up or down as needed. The software as a service approach turns software into an operational expense with predictable subscription costs and the flexibility to adapt as needs evolve. It excels in situations where simplicity and rapid deployment are priorities, though it does mean giving up some control over data storage, customization, and integration with legacy systems. Comparing these three models, the distinction often comes down to balancing control, flexibility, and simplicity. Infrastructure as a service offers the most control and customization, but requires more technical expertise and management effort. Platform as a service provides a ready-made environment for development, reducing operational complexity at the expense of some flexibility. Software as a service delivers immediate functionality with minimal user responsibility, but offers the least ability to tweak or tailor the underlying system. Each model fits different needs and capabilities depending on the organization. It is important to note that the boundaries between these models are not always rigid. New service types such as container as a service and serverless computing further abstract or specialized cloud offerings. These models continue to evolve as cloud providers experiment with new ways to deliver value and simplify technology consumption. Still, for most practical purposes, infrastructure as a service, platform as a service, and software as a service remain the foundational pillars of cloud service delivery. Turning from service models to deployment models, the way cloud resources are provisioned and managed varies widely, with different implications for security, scalability, and efficiency. The public cloud is perhaps the most familiar. In this model, resources are owned and operated by third-party providers and shared among multiple customers, often through vast, geographically distributed data centers. Public cloud services are accessible over the internet and offer virtually unlimited scalability, making them an attractive choice for businesses seeking flexibility and cost efficiency. Because resources are pooled and usage is metered, organizations can quickly scale up or down in response to demand, paying only for what they use. The advantages of the public cloud are clear: no need for capital investment in infrastructure, rapid deployment, and access to a wide and constantly growing array of services. However, this model also means sharing physical infrastructure with other users. While providers invest heavily in security and logical isolation, some organizations, especially those with strict regulatory, privacy, or performance requirements, may hesitate to host sensitive workloads in a shared environment. The private cloud model addresses these concerns by dedicating resources to a single organization. Private clouds can be hosted on-premises, within a company's own data center, or managed by a third-party provider but reserved exclusively for one client. This approach offers greater control over security, compliance, and customization, allowing organizations to design their cloud environment to precise specifications. Private clouds are especially popular in industries such as finance, healthcare, and government, where data sovereignty and regulatory compliance are paramount. However, the benefits of private clouds come with trade-offs. The organization bears more responsibility for managing and maintaining the infrastructure, which can require significant investment in expertise and resources. While private clouds can be highly tailored, they may lack the rapid scalability and cost advantages of public clouds, especially for smaller organizations or those with highly variable workloads. Bridging the gap between these two extremes is the hybrid cloud model. In a hybrid cloud, organizations combine elements of both public and private clouds, creating an environment where data and applications can move seamlessly between the two as needs dictate. For example, a business might run sensitive databases in a private cloud while using the public cloud for less critical workloads or to handle bursts of demand. This approach offers a blend of flexibility, scalability, and control, allowing organizations to optimize for cost, performance, and security based on the specific requirements of each workload. Hybrid cloud strategies are increasingly popular among organizations seeking to modernize their information technology operations without discarding existing investments or exposing sensitive data to unnecessary risk. By leveraging the strengths of both public and private clouds, businesses can respond more nimbly to market changes, support innovation, and ensure continuity even during disruptions. Managing a hybrid environment is complex, however, requiring careful coordination, integration, and ongoing oversight to ensure that data, applications, and security policies remain consistent across multiple platforms. Some sources also discuss a multi-cloud deployment model, in which organizations use cloud services from multiple providers, public, private, or both, often to avoid vendor lock-in or to leverage the unique capabilities of different platforms. This approach introduces additional complexity but can further enhance resilience, geographic reach, and strategic flexibility. The decision between public, private, hybrid, or multi-cloud deployment is rarely straightforward. It involves careful consideration of the organization's needs, regulatory landscape, existing infrastructure, and long-term goals. Security is often a primary concern, as is the ability to scale with demand and manage costs effectively. The choice of deployment model shapes not only the technical architecture, but also the operational culture and strategy of the organization. As cloud computing has matured, the interplay between service and deployment models has given rise to a rich array of options for businesses and individuals alike. There is no one-size-fits-all solution. Instead, the most successful cloud strategies are those that thoughtfully align technology choices with organizational priorities and constraints. For some, that means adopting a software-as-a-service solution to support remote collaboration with minimal fuss. For others, it may involve building custom applications on a platform-as-a-service platform or architecting a hybrid environment that balances agility with control. The evolution of cloud service and deployment models continues to be driven by the needs of users, the creativity of providers, and the relentless pace of technological change. As organizations look to the future, understanding these core models and the trade-offs they entail remains essential for harnessing the full potential of the cloud while navigating its challenges. Whether seeking to innovate, scale, or simply operate more efficiently, the choices made at this foundational level shape what is possible in the digital age. Cloud computing has swept into the worlds of science and business like few technologies before it, transforming how people access, process, and manage information. Its rise has brought a host of notable advantages, but it has also introduced new challenges that organizations must navigate carefully. As the landscape continues to evolve, cloud computing signals an era of even greater innovation, one that will reshape not only technology, but also the very fabric of how we work, collaborate, and solve problems. The most celebrated benefit of cloud computing is its remarkable scalability. No longer limited by the fixed boundaries of physical infrastructure, users can expand or reduce their computing resources almost instantly. This dynamic adaptability is especially valuable for organizations facing unpredictable workloads or rapid growth. For instance, a company analyzing a sudden surge of data can allocate additional cloud servers on demand, then release them just as quickly when the need passes. This elasticity ensures that resources are available exactly when and where they are needed, without the waste or downtime that often plague traditional computing environments. Research highlights how this scalability empowers businesses to respond swiftly to changing market conditions and demands, making them more agile and resilient in the face of uncertainty. Alongside scalability comes cost efficiency, another cornerstone of cloud computing's appeal. Instead of investing heavily in hardware, software, and maintenance, organizations pay only for the resources they use. This pay-as-you-go model reduces upfront capital expenditures and shifts costs to an operational basis, freeing up funds for other priorities. For many, this translates to lower overall information technology spending, with resources deployed more efficiently across the organization. Businesses no longer need to over-provision for peak demand or maintain idle infrastructure during quieter periods. Instead, they can align expenditures with actual usage, resulting in significant savings. This cost-effectiveness has been especially transformative for startups and smaller enterprises, which can now access world-class computing power without the barriers of traditional information technology investment. Flexibility and accessibility further enhance the cloud's advantages. With services delivered over the internet, users can connect to their data and applications from virtually anywhere, using a wide range of devices. This enables remote work, global collaboration, and seamless information sharing capabilities that have become essential in an increasingly interconnected world. The flexibility offered by cloud computing allows organizations to experiment with new ideas, test applications, and deploy solutions rapidly, without the delays and risks of setting up new infrastructure. Whether launching a new service or integrating advanced analytics, the cloud provides a foundation for innovation that is both robust and adaptable. Cloud computing has also had a profound impact on analytics and decision-making. By leveraging scalable, on-demand resources, organizations can process vast amounts of data quickly and efficiently. This ability to analyze information at scale opens up new possibilities for insights and intelligence, driving smarter business strategies and more effective scientific research. Cloud platforms support powerful analytics tools and machine learning services that can be brought online in moments, enabling organizations to uncover trends, predict outcomes, and respond to opportunities with unprecedented speed. Despite these clear advantages, the journey to cloud adoption is not without obstacles. Chief among the challenges are concerns around security, data privacy, and compliance. The very features that make the cloud so powerful, shared infrastructure, broad accessibility, and dynamic resource allocation, introduce unique vulnerabilities. Organizations must contend with the reality that sensitive data is now stored and processed on systems managed by third-party providers, often in locations that span the globe. This raises the stakes for data protection, requiring robust controls to guard against breaches, unauthorized access, and misconfigurations. Data privacy emerges as a particularly complex issue in the cloud. Regulations such as the General Data Protection Regulation in Europe or sector-specific rules in healthcare and finance impose strict requirements on how personal and sensitive information is handled. In the cloud, data may be stored across multiple jurisdictions, each with its own legal and regulatory frameworks. Ensuring compliance with these diverse standards can be daunting, especially when data is replicated or distributed across multiple locations for reliability and performance. Organizations must work closely with cloud providers to understand where their data resides, who can access it, and how it is protected, often relying on detailed contractual agreements and technical safeguards to ensure compliance. Security threats in cloud environments are varied and constantly evolving. Multi-tenancy, the practice of hosting multiple customers' data and applications on shared physical infrastructure, creates risks of accidental data leakage or deliberate attacks if isolation mechanisms fail. Data dispersion, where information is stored across different servers and locations, complicates the task of monitoring and protecting assets. The risk of data breaches is ever present, whether due to external hacking attempts, insider threats, or simple human error. Misconfigured cloud services can inadvertently expose sensitive information to the public internet, and the rapid pace of change in cloud environments can make it difficult to maintain consistent security policies. To address these concerns, organizations are adopting a range of best practices. Encryption of data both in transit and at rest is now standard, as are rigorous access controls and continuous monitoring for suspicious activity. Providers and customers alike are investing in automated tools to detect vulnerabilities and enforce compliance with security policies. Nevertheless, the responsibility for data security is shared, and organizations must remain vigilant in their oversight, even when much of the underlying infrastructure is managed by the cloud provider. Compliance represents another significant hurdle. Cloud users must navigate a labyrinth of regulatory requirements, from international privacy laws to industry-specific mandates. Non-compliance can lead to severe penalties and reputational damage. Yet achieving compliance in the cloud is complicated by the lack of direct control over infrastructure, the complexity of multi-cloud and hybrid environments, and the need to demonstrate that appropriate safeguards are in place. Many organizations struggle to maintain transparency and auditability, especially as cloud services evolve and new features are introduced. Automated compliance tools and frameworks are emerging to help address these challenges, but the landscape remains dynamic and demanding. Other drawbacks of cloud computing, while less dramatic, still warrant consideration. Dependence on reliable internet connectivity can be a limiting factor, especially in regions with poor infrastructure. Technical issues or outages at the provider's end can disrupt access to critical services. In some scenarios, particularly over long periods or for specific workloads, cloud costs may outpace those of on-premises solutions, especially if resources are not carefully managed. Finally, the abstraction and automation that make cloud computing so convenient can also result in a loss of direct control, leaving some organizations uneasy about their ability to intervene or customize as needed. As cloud computing continues to evolve, new trends are shaping its trajectory and expanding its potential. One of the most notable is the rise of hybrid and multi-cloud strategies. Rather than relying on a single provider, organizations are increasingly distributing their workloads across multiple clouds, both public and private. This approach offers greater resilience, flexibility, and freedom from vendor lock-in, but it also introduces added complexity in management and integration. Serverless computing is another breakthrough, allowing developers to run code without managing servers or infrastructure. This model abstracts away operational details, enabling teams to focus purely on writing and deploying applications. Serverless architectures can reduce costs and improve scalability for event-driven workloads, though they also require new approaches to monitoring and security. Artificial intelligence and machine learning are becoming deeply embedded in cloud services. Cloud platforms now offer artificial intelligence-driven tools for data analysis, automation, and system management, making advanced capabilities accessible to a wider range of organizations. Artificial intelligence as a service is an emerging model, providing on-demand access to sophisticated algorithms and computing resources without the need for specialized hardware or expertise. This democratization of artificial intelligence is expected to accelerate innovation across fields as diverse as healthcare, logistics, and finance. Edge computing represents another frontier, designed to bring cloud capabilities closer to where data is generated and consumed. By processing information at or near the source, such as on sensors, mobile devices, or local gateways, edge computing can reduce latency, improve responsiveness, and support applications that require real-time analysis. The integration of edge computing with cloud platforms is being propelled by advancements in fifth-generation connectivity and the growing demand for distributed intelligence systems. Sustainability is also gaining prominence as an imperative for the future of cloud computing. As data centers consume increasing amounts of energy, providers are investing in more efficient architectures, renewable energy sources, and automated resource management to minimize environmental impact. The push for greener cloud services aligns with broader efforts toward digital transformation and responsible business practices. Compliance automation is emerging as a powerful tool to address the growing complexity of regulatory requirements. By embedding compliance checks and controls directly into cloud workflows, organizations can reduce the risk of human error and streamline the process of demonstrating adherence to standards. This trend reflects a broader movement toward greater automation and intelligence in cloud management. Quantum computing, though still in its infancy, is beginning to intersect with the cloud. Some providers now offer access to quantum processors and simulators as cloud services, opening the door to experimentation and research in this cutting-edge field. While practical applications remain limited, the potential for quantum cloud computing to revolutionize areas like cryptography and complex modeling is a subject of keen anticipation. Looking ahead, cloud computing stands poised for continued growth and transformation. Analysts predict that the global market will expand as organizations of all sizes embrace cloud solutions to drive innovation, agility, and efficiency. New service models, deployment strategies, and technological breakthroughs will continue to emerge, reshaping the contours of what is possible in computing. Yet for all its promise, the cloud's ongoing evolution will require careful stewardship. Balancing the pursuit of new capabilities with the imperative for security, privacy, and compliance will remain a central challenge. Organizations must navigate an environment that is at once more powerful and more complex than ever before, guided by a clear understanding of both the benefits and the risks. Ultimately, cloud computing is not merely a shift in technology, it is a transformation in mindset. It invites us to imagine new ways of working, collaborating, and solving problems across disciplines, industries, and geographies. By harnessing its strengths and addressing its challenges, we stand at the threshold of a new era, one where the boundaries of what we can achieve are limited only by our imagination and our resolve to use technology wisely.